Unit 4 Chemistry, Chapter 13, looking at analysis using chromatography. Now you've covered this in Year 11 where you looked at HPLC. There really isn't much more, we're just going to be analysing this again. So let's remember first of all what chromatography is. It's a separation technique, and there are lots of different ones. All of the separation techniques that are called chromatography have a stationary phase, which stays still, and a mobile phase that moves. Okay. They also have a sample that you are separating and a detector, something that measures the separation. Okay. The reason they're separated is because the things in the sample will have a varying adsorbance to the stationary phase and solubility in the mobile phase. So the more soluble they are in the thing that moves, the more they'll move, or the faster they'll move. The more they adsorb or stick to the stationary phase, the slower they'll move or the less they'll move. Simplest is paper chromatography, that I'm sure you're very, very familiar with. Okay, if we had something like paper, which is made of cellulose, which is polar, okay, a substance which is itself very polar will stick quite close to the bottom because there will be strong attractions through hydrogen bonding. Something which dissolves well in our solvent, which would normally be a non-polar solvent, something which dissolves well in that would move a long way up. Okay? You need, therefore, to be able to answer questions about chromatography, to have a good understanding of polarity and intermolecular bonding. Okay? The mobile phase is what moves. Yep. The components are attracted to it by exactly the same type of forces as they were attracted to the stationary phase. Okay? Sometimes your stationary phase is polar, sometimes the mobile phase is polar. Okay. Ultimately, how far a component moves is dependent on its attraction to both the stationary and the mobile phase. So it's a balance of those two. Okay. If we are drawing a chromatogram, then we draw a pencil line, because pencil doesn't dissolve, slightly up from the bottom, so it's going to sit above the solvent. You put your sample on, you place it in the container, and the mobile phase will move up until it gets close to, but not the end, separating the components as we go. Okay. Now, HPLC works on the same principles, but we use it for organic compounds. Okay. And it's a bit more complex, but we've got the same idea. Okay. We have a stationary phase. In this case, it's a column that is packed full of normally little beads. We have a mobile phase, which is a liquid, and it gets pumped through. Okay. High pressure or high performance, liquid chromatography. That P can stand for either pressure or performance. And then here, instead of drawing a pencil line and putting our sample on it, we inject it. Okay? It's going to move through, okay? And it's going to be detected down here. It's very useful for organic compounds because they've got big molar masses, okay, generally bigger than that, and or sometimes both. They decompose when you heat them. So if you took something like glucose, which is only 180 grams per mole, yeah, but we would put it through this chromatogram anyway, because if we heat up glucose, it gets turned into caramel, okay? And we don't want to put caramel into a chromatography machine. HPLC, the advantage of it is it can work at low temperatures. We don't need to heat it up. Okay? The liquid, which is the mobile phase, is what's going to dissolve our organic compounds. Okay? The stationary phase is a waxy porous substance, and the components will adsorb to that. Okay? We have some very small little beads, which maximizes the surface area and therefore gives greater opportunity for adsorption and therefore better separation. Down the bottom, when it comes out, the liquid is going to pass through a UV vis machine. Okay, remember UV vis from back in Unit 2? Yeah? It basically will measure how much light is absorbed, and the more light is absorbed, the more of the sample there is there. Okay? We would normally use this for quantitative analysis, but we can use it for qualitative as well. Okay? To use it for qualitative analysis, we note when we add the substance and when the various parts come out. Okay? The retention time is specific to different substances. Okay? So if it comes out quickly, then that means it didn't adsorb very much, and that would be characteristic of that particular component in there. Okay? The RT, or retention time, is going to depend on the structure of what you've got, your mixture, or the particular components in the mixture, the temperature, how big the column is, because the bigger it is, the longer it takes, and the nature and chemical structure of the stationary phase. Okay? So each of these peaks here is specific to a different compound, okay, under those conditions in that chromatogram machine. And so if we had some reference values, we could compare to them and identify therefore whether it is the right substance. We can also do quantitative analysis. Now, quantitative analysis is finding how much of something we've got. So under each of those peaks, we can find the peak area. And the peak area is proportional to the concentration. But we need to compare that to some samples of known concentration of the same substance. So we draw up a calibration curve, okay, which is going to look something like this. So these are all our standards. Okay. Then we would put our unknown in. And for our unknown, we wouldn't know its concentration, but we would know its peak area. So we'd read off the peak area and read down to find the concentration. Simple as that. And then you check in your question to see whether you'd done any dilutions or if there were further calculations that you needed to do.